I would like to welcome you to this session. I'm Ronald Ddungu, a teacher of physics and maths at Gayaza High School, and today we want to study pressure in liquids, one of the physics topics within the Senior 2 syllabus. When you move around on many buildings, you do find many water tanks raised, and from here we can see an inlet pipe bringing in water at the top of the tank, and on the side we have an outlet tap just below the tank. The question that would arise is why the inlet pipe is on top and why the outlet tap is below. And that is where we are going to concentrate our study to see what is it all about in physics and pressure in liquids, about why the engineers place the inlet pipes and outlet pipes like that. We will take a look at yet another tank to see the design there. In the same design, the engineers seem to have a consistency. The bigger pipe at the bottom of the tank is the outlet pipe, and the smaller pipes at the top are the inlet pipes. Our question is, why the consistency of inlet pipes to be at the top and outlet pipes to be at the bottom? We will now go into the physics laboratory and depict the situation in this tank to see what is all about the pressure in liquids that requires an engineer to place the outlet pipe at the lower end of the tank. Where we are going to have some form of a tank using our day-to-day containers. If this was your tank, we want to answer the question, why must you put your outlet pipe at the bottom and put the inlet pipe at the top? And we are going to study the physics of pressure in liquids. So I will turn on the inlet tap. When I have three pipes picking water from this tank, the one at the bottom is seemingly throwing the water at a greater distance than the one at the top and even the one at the bottom. Why is this so? The reason why we are seeing that the one at the bottom is throwing water at a greater distance is because of what we would call the kind of pressure of water at the bottom as compared to the water at the top. Now, the quantity of water sitting on this pipe is much, much bigger than the quantity of water sitting on top of this pipe here. And that means there is a greater force resting onto this level than the force resting onto this level. As we discussed earlier on, pressure is all about force acting per unit area. When you get a greater force acting per this surface area and a less force acting per the same surface area, you do find that the greater the force, the greater the pressure. So you will have a greater pressure at the bottom, and water coming out here is at a high pressure, and it can travel longer distances than the water coming out at this level. So it therefore means when the engineers are designing their tank, they must make sure that they pick the water from the tank using the lower end, and they bring in the water from the top. So this explains what is happening in those tanks we saw. So when you become engineers tomorrow, we hope you will not make a design of a tank that will not give you the best results. You must take into account the pressure of a liquid, depends on the depth of the water from the surface of the object. The deeper the end, the greater the pressure. We will now turn to something different. We talk about pressure. Wherever we stand, we experience a lot of pressure. As an individual, there is pressure surrounding you due to the air molecules within your vicinity. We want to show that actually there is pressure that exists around us, and why must we have this pressure? Of what importance is it? Now we are going to carry out an experiment to show that actually pressure exists within the atmosphere. And using our containers here, we are going to fill them with hot water. That hot water will help us to drive out all the air that might be within here and set some pressure within the containers. Now you have to do it carefully. I also have another. Now, we are going to watch the shapes of these containers. Because of the steam in there, you can see the kind of shape they are undertaking. But then when we pour cold water, you see the containers are collapsing. They are collapsing. They are not the same containers we had. And we would like to explain why these containers are collapsing. Now, originally, when we had hot water within the containers, we built some kind of pressure in there. Now, when you pour cold water and you see the crumbling is simply because there is a greater force now from outside than what is inside. Originally, when you have a container like this, there is air inside and there is air from outside. Now, the pressure from inside is balancing out with the pressure from outside. And that means you keep a stable position simply because you have the same pressure from outside. But when do we know that actually there is pressure from outside? That is when we reduce the pressure from inside, not to look like the pressure from outside, and then we pour cold water. Now, when we pour cold water, the crumbling shows us that actually what is outside now is much, much greater than what is inside. What is inside cannot keep in place the usual shape of the container. And that shows us that there is some pressure from outside. That pressure from outside is what we call atmospheric pressure. So around us, there is a lot of atmospheric pressure, and we are now going to look at the applications of atmospheric pressure. I'm ready to take my drink, but I must find ways and find out why am I able to draw the drink through this straw. Now, when you undertake to take soda through a straw, you will not get the soda rising up unless you pull on the straw. Now, when you pull on the straw, all you are going to do is you will pull away the air within your mouth so that there is less pressure within this straw. And as such, atmospheric pressure is acting on the open surface of the bottle. That atmospheric pressure will definitely be much higher than the pressure within your mouth and within the straw. And therefore, the soda will run into the straw. The soda runs into the straw by means of the atmospheric pressure, which pushes it and finds less pressure within your mouth and within the straw, and hence the water or the drink is able to rise within the straw. At atmospheric pressure, as an individual, we have blood within the body which has pressure, and there is atmospheric pressure from outside, so the blood pressure and the atmospheric pressure balance out. But if you were to die, then the pressure within the body reduces because your blood goes cold, and therefore atmospheric pressure from the top is much greater than the pressure from inside. And when you touch the skin of a dead person, then you are able to push the fingers through, simply because now you can't have pressure from inside, but there is atmospheric pressure from outside. All those examples show us why atmospheric pressure exists and how we can make use of atmospheric pressure to go on with our day-to-day living.